Good day, everyone, especially to our teacher. We are the group 2. In this recorded video, content the topic all about the Milky Way and normal spiral galaxy. Me and my group mates explained about on it.
In the formation of single galaxy, it has a dominant theory called bottom-up formation, which means that smaller clouds merge and form a larger structure that then becomes a galaxy. And the flat disk appears because of rotation and conserving of angular momentum. The modern infrared and radio observation form the current model of the Milky Way galaxy. With that observations, it showed the two spiral arms with concentration of young hot O and B stars and that it makes confirm as a spiral galaxy. Disks do not rotate like a solid body. Instead, material that is closer to the center takes less time to complete a revolution around the galaxy than does material farther out in the galaxy. For example for that is when the bulge in the center of a spiral galaxy is elongated instead of spherically symmetric, as seems to be the case for most spiral galaxies. Then the bulge produces a gravitational disturbance in the disk. As the disk rotates through this disturbance, repeated episodes of star formation occur and more stable spiral arms form. Any disturbances such as a sequence of stellar formation events that are sometimes found drawn out in a near linear pattern will eventually take on a spiral shape, simply because of the differential rotation. As time goes by, there were some new discoveries about the shape of our galaxy and even its major features. There is a two major spiral arms, the Scutum Centaurus arm and the Perseus arm. There are also the several smaller arm segments like Orion's spar that contains the Sun and Solar System. The Milky Way galaxy's structure is fairly typical of a large spiral system. It consists of six parts. Nucleus, the very center of the galaxy that lies a remarkable object, a black hole. Central bulge, located in the surrounding of the nucleus. Disk is the most conspicuous part of the galaxy from a distance that can be thought as the underlying body of stars upon which the arms are superimposed. Spiral arms, the spherical components that contains the variables and dwarf stars, the massive halo, which is the exterior of the entire visible part of the galaxy. And now we will discuss the discovery of Cepheid variables in other galaxies and how distances to galaxies are estimated through the use of standard candles. Cepheid and RR Lyrae, who are candidates for standard candles, are both pulsating variable stars, which it is actually changes its diameter with time. RR Lyrae stars make it easy to determine the distance to another galaxy. Just measure the average apparent magnitude of the variables and compare the known absolute magnitude. A typical RR Lyrae has a luminosity perhaps 50 times greater than the Sun. They use this light curve that which is about a graph that shows how the brightness of a variable star changes with time. The maximum of the light curve will be the greatest brightness and the minimum is the point where it is faintest. As the star pulsates, it also changes its overall color, indicating that its temperature is also varying. The importance of Cepheid variables lies in the fact that their periods and average luminosities turn out to be directly related. That is why the relations allow you to essentially read off how bright the star really is. Then the astronomers can then compare this intrinsic brightness with the apparent brightness of the star. As we saw, the difference between the two allows them to calculate the distance. There's also some guide to how to use a Cepheid to measure. First is find a Cepheid variable star and measure its period. Second, use the period luminosity relation to calculate the star's luminosity. Third, measure the star's apparent brightness. And then lastly, compare the luminosity with the apparent brightness to calculate the distance. Cepheid and RR Lyrae stars are two types of pulsating variable stars. Light curves of these stars show that their luminosities vary with a regularly repeating period. RR Lyrae stars can be used as standard bulbs, and Cepheid variables obey a period luminosity relation, so measuring their periods can tell us their luminosities. Then we can calculate their distances by comparing their luminosities with their apparent brightness, and this can allow us to measure distances to these stars out to over 60 million light years. Using this period luminosity relationship to find the luminosities of RR Lyrae stars in globular clusters. Then use the inverse square of law of radiation to combine these luminosities with measured brightnesses to compare the distance to globular clusters. And that's how globular clusters used to determine the size of the Milky Way galaxy.
Hi everyone! So one of the most interesting subtopic of the Milky Way, a normal spiral galaxy, is the dark matter. We all know that it is a mysterious substance thought to compose perhaps about 27% of the makeup of the universe. So what is dark matter? Dark matter is formed of particles, and it is not just an ordinary atoms. Second, it doesn't absorb or emit light. In other terms, it does not interact with electromagnetic force. Third, it has an attractive gravity which keeps the stars swirling out into space as well as gives speeds to galaxies' rotation. And lastly, dark matter binds or holds the universe. Evidence of dark matter within galaxies. So 21 centimeter line of hydrogen is a power tool used by astronomers. To prove the structure of the Milky Way, they use 21 centimeter line of hydrogen because it can penetrate the clouds of interstellar dust particles that obstruct optical observation deep into galactic center and thus allows the mapping of the galaxy's spiral structure. So based on this figure, a duple velocity measurement based on observatory of 21 centimeter emission, the velocity differ as a comparison of redshift and low shift in the plane of observation. Toward the galactic center, astronomers see gas clouds moving toward Earth is blue shifted, whereas the gas clouds moving away from Earth is red shifted, and it is a pattern of the rotation of the velocity of gas in a disk. Take note that from the Earth's perspective, within the solar system perspective, the revolving disk signature is evident from both sides of the street of galactic center. This 21 centimeter line also enables astronomers to measure the galaxy's rotation curve, and the Milky Way galaxy has a flat rotation curve that lead astronomers to conclude that the masses of spiral galaxies consist mostly of dark matter. At this figure, the rotation velocity is plotted against distance from the center of the Milky Way. The most distant point comes from measurement of the orbit of the Large Magellanic Cloud. So, the nearly flat rotation curve indicates that the dark matter dominates the outer parts of the Milky Way. So, if visible matter dominates the inner part of the Milky Way galaxy, the dark matter dominates the outer parts of the Milky Way galaxy. It also accounts for the majority of galaxy's mass, or in a simple term, the Milky Way's mass consists mainly of dark matter. If we're thinking what really dark matter is responsible for the way galaxies are organized. Through its gravitational effect, it binds the stars and planets within a galaxy. So why is it significant to studying dark matter? So the significance of studying dark matter is that it could help us to understand the size, shape, and future of the universe. And the amount of dark matter could help us to know whether the universe is continuing to expand, or it is expand to a point and then collapses, or it expand and then stop when it reaches equilibrium. So that's all. I will gonna give the floor to the next reporter.
Don't you know that you can determine the age of the star depending on its color? Stars appear to be similar at first glance. Twinkling dots scattered throughout the sky. You can see the different colors if you study and look carefully. When using binoculars, you will notice that they have various of colors. This also made spectroscopy absolutely relevant. It is a study of a star's absorption of light or radiation. Stars are hot balls of gas, so they give off continuous spectrum. They emit light at all wavelengths. However, stars have atmospheres, which are the thin layers of gas that lie above the denser core layers. These gases absorb light below the least massive elements at certain wavelengths. Cecilia Payne-Gaposchkin stated that the stars are overwhelmingly composed of hydrogen. Helium is the second most abundant element of it. As stars become older, they run out of oxygen to burn, reducing the quantity of hydrogen they release. Thus, younger stars look bluer and the older stars appear redder. Through this, a star's color can tell us something about their age. Like our sun. The sun has the surface temperature of about 550 degrees Celsius. It is in the middle part of the main sequence of the HR diagram, which means that the star in our solar system is younger and yet to die.
Good day, my name is Crystal Andy Cibalios, and I'm going to report the magnetic fields and cosmic rays fill the galaxy. In general, charged particles spiral around magnetic fields, causing a net motion along the field rather than across it. In addition, magnetic fields cannot freely escape from a cloud of gas containing charged particles. The dense clouds of interstellar gas in the midplane of the Milky Way anchor the galaxy's magnetic field to the disk. In the image, the weight of interstellar clouds anchors the magnetic field of the Milky Way to the disk of the galaxy. The magnetic field, in turn, traps the galaxy's cosmic rays. Some cosmic rays have enormously high energies. In contrast, the most energetic cosmic rays are 10 trillion times as energetic as the lowest energy cosmic rays, and they move very close to the speed of light. These high-energy cosmic rays are detected from the showers of elementary particles that they cause when crashing through Earth's atmosphere. Astronomers hypothesize that cosmic rays are accelerated to these incredible energies by the Hawk waves produced in the supernova explosions. Cosmic rays are trapped by the Milky Way's magnetic field. The galaxy's disk is illuminated by synchrotron radiation spiraling around the galaxy's magnetic field. Nonetheless, the high-energy cosmic rays are far too fast to be contained by the gravitational force of their parent galaxy. Any cosmic rays that formed in the Milky Way would soon begin to stream out of the galaxy and into intergalactic space. As a result, it is likely that most of the energetic cosmic rays reaching Earth are the result of energetic things happening outside the Milky Way galaxy. High-energy electrons and other subatomic particles. These are only a few high-energy electrons and other subatomic particles. The particle energy range of cosmic rays is enormous. The lowest energy cosmic rays can be observed by astronomers by means of interplanetary spacecraft. These cosmic rays have cost energy as low as 10 to 11 joule, corresponding to the energy of a proton moving at a few tenths of the speed of light. Milky Way galaxy magnetic field and the cosmic ray energy are equal. Both are comparable to the energy present in other energetic components of the galaxy, such as interstellar gas motions and the total energy of electromagnetic radiation within the galaxy. This similarity in energy level suggests that they are all connected. One possible scenario is the supernova explosions accelerate cosmic rays, steering the interstellar medium and generating turbulent motions and the magnetic field. The pressure from all of these components support the disk and keeps it vertical equilibrium. Magnetic fields trap cosmic rays within the galaxy. These magnetic fields trap cosmic rays within the galaxy. Despite their name, cosmic rays are not a form of electromagnetic radiation. These are charged particles moving at nearly the speed of light. They were named before their true nature was revealed.
The Milky Way hosts the supermassive black hole. Supermassive black hole at its center known Sagittarius E star. Sagittarius E star is the location of supermassive black hole. The Milky Way galaxy contains some 100 billion stars. Black holes form after massive star run of fuels, a star to collapse and as a supernova. Significance of studying supermassive black hole. Explain how the universe works on. Critical part of the formation and evolution of galaxy. The largest and the smallest scales. To find the beginning of black hole and also determine characteristic of supermassive black hole. Observation of supermassive black hole. The Chandra X-ray Observatory. The Chandra X-ray Observatory has detected more than 9,000 X-ray sources within the central region of the galaxy. These include frequent short-lived X-ray flares near Sagittarius E. The Fermi Gamma Ray Space Telescope. The Fermi Gamma Ray Space Telescope has observed gamma ray emitting bubbles that extend 8 kp above and below the galactic plane. The Event Horizon Telescope. The Event Horizon Telescope is an active program that directly observes the immediate environment of black holes. Event horizons such as the black hole at the center of the Milky Way. The Spitzer Space Telescope. The Spitzer Space Telescope, formerly Space Infrared Telescope, facility was an infrared space telescope launched in 2003. Operations ended on January 30, 2020. Spitzer was the third space telescope dedicated to infrared astronomy. Optical observations of Hubble Space Telescope. The Hubble Space Telescope mirror-based optical system collects and focuses light from the universe to be analyzed by science and guidance instrument. The optical system, called the Optical Telescope Assembly, gave Hubble a unique view of universe by gathering infrared, visible, and ultraviolet black hole in this observed AGN. The time variation of AGN. The Eddington luminosity argument. Lamps in the early universe. The stellar seed model. Collapse of the whole star cluster. An active galactic nucleus, AGN, is compact region at the center of the galaxy that has a much higher than normal luminosity over at least some portions of electromagnetic spectrum, with characteristic indicating that the luminosity is not preceded by star. Thus, excess non-stellar emission has been observed in the radio, microwave, infrared, optical, ultraviolet, X-ray, and gamma-ray waveband. A galaxy hosting a AGN is called an active galaxy. The non-stellar radiations from a AGN is theorized to result from the accretions of matter by a supermassive black hole at the center of its host galaxy.
Let's now move to the last topic of the Milky Way, and it is all about Milky Way offers clues about how galaxies form. Did you wonder how galaxies form? One of its clues is the distribution of stars of different ages with different amounts of heavy elements. So information about stellar populations hold vital clues, and by determining the distribution of stars and looking for the oldest and younger stars, we can get clues about how galaxies form. Another clue is by studying other galaxies at different distances, and this indicates that some galaxies have formed within the past few billion years, and it is relatively in cosmic terms. Next is their supermassive black holes. So by measuring the masses of supermassive black hole and the bulges of their host galaxies, it can lead to the birth of how galaxies form. Next is the merger history. There are computer simulations that suggest such merger could cause the spiral arm galaxy. Next is the properties of globular clusters and high-velocity stars in the halo of the galaxies indicate as the important clues of how galaxies form. Astronomers believe that Milky Way started when gas within a massive clump of dark matter fell into a vast number of small proto-galaxies where new stars formed, creating extensive spiral arms filled with colonies of stars. The local group of galaxies. Local group is part of the local supercluster called Virgo supercluster, containing over 100 smaller groups and clusters of galaxies. As you can see in the figure, that is the Virgo supercluster. It includes the two giant barred spirals, naming Milky Way and Andromeda galaxy. Triangulum, an unbarred spiral, is the third largest galaxy. It is first identified by Edwin Hubble in 1936. Hubble labeled 12 galaxies as part of the local group, and now astronomers count at least 50 galaxies in local group, many of which are tiny dwarf galaxies. Milky Way is surrounded by more than 20 satellite dwarf galaxies, which are smaller galaxies that orbit around it. The most prominent of these are the Small Magellanic Cloud and the Large Magellanic Cloud, each around a tenth size of the Milky Way, which can be seen with naked eye and observable from the southern hemisphere. Therefore, Milky Way offers many clues about the way galaxies form, but much of what astronomers know, the process comes from the looking beyond the local group, images of distant galaxies, as well as observations of the glow left behind by the formation of the universe itself. Will Andromeda and Milky Way collide? We all know that Andromeda and Galaxy are the two largest galaxies in the local group. Since Hubble noticed over a century ago that Andromeda spectrum was blue-shifted, indicating that it was nearing the Milky Way. This led astronomers wondered if and when Andromeda and Milky Way would collide and form merged galaxy. So astronomers concluded that Andromeda and Milky Way collide head-on about 4 billion years. And this event will really take billions of years, since simulation shows that this will be an incredible event that will take several billion years to play out of completion. Collisions of galaxies will occur before the Sun runs out of hydrogen in its core, while it is likely that the Sun's luminosity will increase sufficiently then to affect Earth's habitability. Therefore, collisions and mergers between these galaxies likely to happen in the past, and the merger with the Andromeda galaxy may be part of the Milky Way's future. And that concluded our report in this topic, Milky Way, a normal spiral galaxy. And thank you for listening.